Right, welcome to the second morning session. We have two speakers. So the first one is Syed Hassan from Institute of Mathematical Sciences, Chennai, and he'll be talking on algebraic spin liquid in Kitaev Hubbard model.
So I would like to thank first Subruto to invite me and press me to give a talk. Otherwise, earlier I was thinking I will not come here. So today I am going to talk this algebraic spin liquid phase in the Kitaev Hubbard model. So the issue what we are going to deal here is algebraic spin liquid. So first let us try to briefly understand what are spin liquids. So this is whatever I am going to explain here is not for the expert people, those who are entering in the field or first year graduate students. For them, I am going to use a lot of jargon. So I am asking apology in advance. So what I am going to tell you that condensed matter system is a very simple system, very simple system. Building blocks is just lattice plus electrons. Then where is the problem? Problem in the appearance. Device or the observer what we are, we see things and that is the appearance. So as far as the system is concerned, is a electrons plus lattice. So you can say that what is happening there. So it is not like a very strange things. If you look at football game, ground is same, 11 players are there, but you can see a Spanish football, then result will be different. You can see a Brazilian football, result will be different. You can see Italian football, result will be different, right? So I am not going to detail what lattice is doing, but what I am going to tell you, this lattice is providing a home for the electrons to play game inside there. And the way they play the game, many things appears. And many things appear and you see, and many phases is the outcome of that game. So the problem is this, when you, the condensed matter system for the outside is a deterministic object, a real object, but inside what is happening we don't know. So I don't treat electron as an object, but I treat electron is a collection of some attributes. So let us give attributes charge and spin. Electron is nothing but charge and spin, and these attributes playing a game called what the lattice provided you in this big palace, big house. And if you tune this parameter, collective attributes may be different. So you can say, how can it be possible? So Marx pointed long back that quantity can be transformed in quality. So it is a problem of quantity, large quantity of electrons and many kind of a quality appears. So it is the way you want to look, you see the system. So to understand these things, let us try to model it. So the game of electron you can construct by just collection of electrons which is hopping in this big house what we call lattice, and for that this electron is moving, this kid whatever children what you call here in that home is moving, and that is what here is the kinetic energy of that electron. Since those electrons can interact, for that interactions you can add here this term. So this is a Hamiltonian what we call Hubbard model. This Hubbard model Hamiltonian is living in a space or home what we call lattice. So you put this model in a triangular lattice or Kagome lattice or all sort of a lattice. Then let us start to understand the rule of the game and the result of the game. So what happens? So as I told you that electron is nothing but a attributes, collection of attributes. When the interaction between the electron is a small, electron try to forget its spinning degree of freedom and manifest just charge degree of freedom. This is a jargon, so you cannot catch me there like a right word. For this manifest just charge degree of freedom, and that what you call in some sense a metal. But as you keep increasing this term u, this u, what will happen at very large limit, this electrons will try to forget its charge degree of freedom, and it will manifest in some sense just spin degree of freedom or spin attributes. So, what happens to charge? You can think charge become lazy, or charge is in the real term what you say charge is gapped out. So, charge becomes really lazy, they do not play game there. In that regime in large U, the game is playing just attributes called spin. So, what is happening? These two attributes and charge and spin are entangled. As you change the parameter, there is a well defined things called metal, there is a well defined thing called attributes called insulator, which you are governed by this. But there is a state of electron what we call crazy state or mentally retarded state of electron. That is the most difficult state to understand. What is mentally retarded or crazy state? You imagine a person, he is laughing and he is also angry, and at the same time he is kind and he is also violent. Can you imagine such kind of a person? If you are imagining, you will be shocked and you will think that person is mentally retarded. So, it might be possible. So, when you keep tuning this parameter called U, there will be a window of this parameter. Electrons are hesitant, electrons are confused, and electrons. So, because these two attributes started become very violent. So, that is also a physics, very difficult physics to understand. So, as you know that when U is large, relevant attributes which game in that house playing is spin. So, you can construct, if you want to understand the rule of the game, construct a spin Hamiltonian on this house and try to find states, what kind of the emergent attributes are there. So, when U is large, real attributes, the game playing attributes are there is spin. So, you can construct a spin Hamiltonian and then construct the palaces, big palaces like extended up to infinity is a Kagome lattice, triangular lattice, and then honeycomb lattice. So, only difference between the football game and this game here, you see this is a house, electrons are residing and playing a game, but this house is very important. They are also influencing the game, right. This is the very important point to understand. So, although it looks like a rest, nothing playing a role, but you take this attributes, place here, and then you will find what kind of the house you have, different kind of attributes will emerge. This is one thing. So, for the time being, what we are interested in, imagine then your parameter called U is very large, relevant attributes of electrons are spin. So, you can construct a spin world or place that spin world there. Then you ask, these attributes are how they are organized, what kind of the symmetries of these attributes, what are the emergent after this attribute, their new attributes may appear. If you know all these things, you can define a new world like the world you earlier defined in the case of metal, semiconductor, insulator. You can define like a spin kind of a metal. See this word what we are using, as I told you, is a jargon. You can define a spin semiconductor, you can define a spin insulator, and so on. It depends upon if you understand what are the emergent attributes of the underlying this spin attributes. So, how can you define a spin liquid? A spin liquid is exotic new phase of a matter. This is a little problematic word nowadays. You cannot say new phase of a matter. When you want to claim new phase of a matter, you have to search a literature, whether it was done in Babylon or not, whether it is done in Aztec civilization or not, whether it is done in Maya civilization or not. If you are confirmed that they have not done, then you have a right to write a new phase. So, I think condensed matter people either ignorant or too smart that they write such kind of things. So, we should be careful using such kind of a word. So, let us believe that we are ignorant. So the exotic new phase of a matter. Then What is this? We said that suppose these attributes are not well organized, or in this not is some kind of order, but as I told you that this phase charge is lazy. Charge is lazy means charge gapped. Charge is not playing role. In some sense, that you call Mott insulating. So, the spin are not ordered. System is a Mott insulator, means there is no magnetic order down to the lowest temperature, and this is the same thing that no magnetic order. He calls the spin is in a disorder phase. So, this is one of the definitions of a spin liquid. Many definitions exist, and you can adopt any definitions. This is the simple definitions which I am adopting. But in the literature, if you will listen the talk of this Professor Senthil, he will give you in more detail what is happening, this game of this electron playing, and what kind of the internal degree of freedom and what are the emergent degree of freedom, that will identify all these kind of a spin liquid, short range RVV spin liquid, algebraic spin liquid, chiral spin liquid, U1 spin liquid, SU2 spin liquid. So, as I told you, the world, the game in that world playing a spin, charge or lazy object, and what kind of the game, it depends upon whether it is a tiki-taka game they are playing, or Brazilian game playing, or the Italian game playing, all sort of a game, whatever the game you can think, you can identify this. Okay, thank you for pointing. Yeah, I will. Next talk definitely I will do. So, SU2 spin liquid. Okay, so this kind of phase what we are talking is spin liquid phase, whether it is a discovered now or discovered in a Babylon civilization or Aztec civilization, we are not bothering about this. Whatever we discovered, we are claiming here such kind of a quantum spin liquid phase in a different kind of houses like Kagome lattice, triangular lattice. This compound makes a house which I am calling triangular compounds, or Kagome lattice, or like a sodium iridate, like three dimensional hyper Kagome lattice. These are compound where we claim that a quantum spin liquid we have found. But as I told you that if you want to understand spin liquid and the only relevant degree of spin liquid, you go in a very large U limit. The game what spin play, you allow just super exchange. This electron can come and hop, and such kind of a model is Heisenberg model. You place that Heisenberg model and do this. But as I told you that you are tuning, the attributes which are entangled, they are becoming violent and they separate, or sometime charge gapped out and the low energy is become like spin. So, if you want to understand that theory, you have to do in the context of Hubbard model. So, people tried Hubbard model on a square lattice, and Hubbard model on a square lattice, you do not get such kind of phase. You will get metal to antiferromagnetic insulator. But if you take a frustrated square lattice, means that you have a nearest neighbor and next nearest neighbor. These people have done this work, that if you want to look a phase diagram, so when U is a small, relevant attributes what you have is charge degree of freedom. This what we are calling a metal here. Then you have antiferromagnetic insulator, then antiferromagnetic insulator of second kind, then you have a stripe phase. But there is a broad range from here to here, what you find a spin liquid where they claim that this they form a spin-on Fermi surface, and so this is a gapless spin liquid, and their quasi-particle description exists here. Similarly, people also tried same thing on a triangular lattice, TT prime triangular lattice. What they find, metal to a spiral and then spin liquid phase, if you tune this parameter called T prime to T. So, Hubbard model on different kind of a home or different kind of a palace, if you want to tune the parameter, what you will find a different kind of a phases, and one of the phase what you see at a large u is a spin liquid phase. But in 2010, there was a very interesting paper came into the market and published in the Nature. What was that paper? Was this observation of theoretical observations of, or simulations in the computer, whatever you call, theoretical observations of spin liquid phase on honeycomb lattice. Why it is so surprising? Surprising is this honeycomb lattice is frustrated. People up to now, those who have invested lot of time and lot of energy, they found the spin liquid in frustrated system. So, this was the first example they have seen spin liquid phase in unfrustrated system. But the old crow of the condensed matter physics, Sandra Sorella, were not happy. How can it be possible that this phase may occur in this system? So, he adopted the same variational Monte Carlo and repeated the calculations and went up to the larger system size. This calculation was done 700 sites, and Sandra Sorella went up to 3000 sites, and they found this does not exist. At the same time, mostly there are 2 months, 3 months this, we also refuted that such kind of thing cannot happen. So, our method was a varieties of method we applied, the cluster approximation, which I am going to explain here, cluster dynamical mean field theory, cluster dynamical impurity. Using all these varieties of method, we showed that such kind of a phase cannot occur in honeycomb lattice, and Sandra Sorella used a quantum Monte Carlo. But what I was interested, can I find any model on honeycomb lattice which can give directly metal to insulator, and that insulator should be not antiferromagnet or all sort of such kind of things. We want a kind of spin liquid phase. So, we have a history, and through the history you learn. So, what was the history? The past lesson, the guy called Kitaev, he constructed a very beautiful model called Kitaev model, and they showed that Kitaev model is exactly solved, and Kitaev model actually supports spin liquid. So, what we thought that can we construct a Hubbard model which can give a Kitaev model. So, if you have a Hubbard model and large U limit can give a Kitaev model. So, if such kind of Hubbard model exists on honeycomb lattice, what are the phases, what are the appearance you can see there. But fortunately, this model was proposed in the context of optical lattice by Daimler and his group, and they showed that you can construct really such kind of a Hubbard model which can give you Kitaev model. So, what is that model? Let me explain. So, I will come this what is as algebraic spin liquid, but so Kitaev model is, what is Kitaev model? Is nothing but first consider you have a honeycomb lattice, and on this honeycomb lattice allow electron to hope with hopping amplitude T, and you know this is a famous looks like a graphene, and if you want to find what is the dispersion relations, dispersion relation is here, you find a 2 Dirac points. Kitaev model is on the top of this hopping you allow a next hopping like a T prime, which in the z direction is a spin, the z spin is hopping, and the y direction this is like a spin projected hopping. In the along the y directions, projected spin hopping, and x. So, x and y z are just convention, you can change whatever you like. If you do it, if you can think that this, you are actually some sense breaking the spin degeneracy what existing in the honeycomb lattice or graphene. So, what you will find that 4 bands, as you keep this parameter T prime equal to 1. At T prime equal to 1, you have a 4 band, 1, 2, 3, 4 bands. So, the parameter what at this model is a T prime, at T prime equal to 0 is graphene. As you keep changing T prime, it will this degeneracy in this band will split, and you are saying this degeneracy at splitting, and you are clearly seeing the 4 bands at Tp equal to 0.5 and Tp equal to 1, the clear separation between the bottom band and the third band, and still a Dirac points you have. But this has still a large other kind of a physics which I have discussed in the last meeting. I am not going to highlight here. So, I am going to tell you that this model, Kitaev model in the presence of U term is a breaks time reversal, only restored time reversal symmetry when of course, it is a very T prime equal to 0, it is a graphene. Under charge conjugations, it is also not invariant, but combination of a charge and time reversal, this Hamiltonian is invariant. So, I want to study this kind of a hopping on honeycomb lattice, means Hubbard model. That model we called the Kitaev Hubbard model, but after we wrote a paper, the other group from MIT, they also wrote a paper. I am pointing in this meeting reason is this, they say we call Kitaev Hubbard model. I said fight, we have already given a name Kitaev model. So, I am going to solve this problem using a cluster method, and this is a little bit technical. So, I want apology because it is needed, because this kind of phases what we are trying to find is very difficult to find in a non-perturbative way. So, the method called quantum cluster method exists in varieties in the literatures. So, I am not going to discuss all those methods, but simple method is called cluster perturbation theory. Then there is other name is called VCA or variational cluster approximation, cluster dynamical mean field theory, and there is a new method is emerging in from the chemistry world is called density matrix embedded theory, which use really heavy idea of this quantum entanglement. That I am not going to discuss here. And then I am there is other method pioneered by Professor H.R. Krishnamurthy and Professor Mark Jarrell, DCA. The story when DCA was reported first, when it was sent, it was rejected in PRL, published in Rapid Communications. After few months or 6 months later, Kotliar and other group given a real space theory of this that is called cluster dynamical mean field theory, that was published in PRL. Okay, so what is the cluster perturbation theory? So, the model is here Hubbard model, and you know you have only 2 parameters, hopping and Coulomb interaction or Hubbard interaction U. When you turn off U, problem is exactly solved. When you turn on when you turn off T, then also problem is exactly solved. So, what we can do varieties of perturbative method. When U is small, you can do weak coupling expansions. When U is very large and T is very small, you can do a strong coupling expansion. So, the reference Hamiltonian in the strong coupling expansion, it is your atomic Hamiltonian H0, and you do the perturbation with respect to this. But the cluster perturbation is a generalization of the strong coupling theory on the cluster. So, what is the method? You have this cluster, and on that cluster you have this lattice, on that lattice this Hamiltonian is sitting. You think a super lattice of such kind where each point is made up of the 4 sides. So, this is the same thing, but you are doing a super lattice where each point, I am calling this as a point which has this contains 4 points of original lattice. So, now let us rewrite Hamiltonian in terms of H prime, that this H, the Hamiltonian H prime I am calling Hamiltonian sitting on this cluster, and this broken bond, right, what you are seeing, we can club into the term called V. So, you are writing your Hubbard model in terms of H prime is a sum over all cluster what you have here, and V is just this term. So, now since we are interested in the perturbations, turn off V, if you turn off V, all clusters are decoupled. So, cluster is just 4 sides. So, So, you can exact diagonalize and you can compute the green function. Then do a perturbations and perturbation turn on this perturbation and then ask lowest order, and in the lowest order you can compute a green functions, where V is just a matrix. And using this method you can compute a self energy and many other things. And this method so you can see in this method what you are computing green functions. Green function of the superlattice, where k what you are seeing is a k of the superlattice, because going from here to here translational symmetry is broken. But if you want to see the if you want to match the experimental result, then you have to restore the translational symmetry. How do we restore translational symmetry? After computing this green functions of the superlattice, we just periodize these green functions, and that periodization is this. The periodization we do in such a way that this sum rule, the density if you integrate the spectral function should come 1. So, we say that this is one of the periodization, we use this. There are other people who use the periodization on self energy, that we do not think is a correct way, because if you take a green function periodization and take a large value of u, you should expect a gap in the spectral functions. So, you are getting a gap here, but if you do a periodization on the self energy, you cannot see the gap. So, this periodization of self energy is correct. But as you see, this is a perturbations theory, and you are interested in some kind of a broken symmetry phase, like a antiferromagnet, D wave, various kind of a superconducting order parameter. This method cannot work, is incapable. So, how to solve this problem? You can say, oh, you can solve, just turn on some kind of a Weiss field, which looks like a staggered magnetization, if you are interested in a staggered magnetization, and put on the cluster and do whatever you do. But the question will come, how will I update this M? You cannot update. So, the problem how to update was done by Pothoff. The method is called self energy functional approach. That method is also very important, because that method unified all class of cluster methods, whether it is a cluster dynamical mean field theory or the method what we are using, except the method which was developed by my supervisor, Professor H.R. Krishnamurthy, because he is a philosopher. That is why he cannot make that thing in this same thing, because that should be a different, distinct, right. So, this method is what? So, it is a very known functional, this is called grand canonical function potential. If you look this, what you find, this is G is a green function of your system, not interacting green function of system. So, this functional omega is entirely a functional of G and depends upon a parameter T, and that parameter comes here just via non-interacting green functions. So, but most interesting feature of this functional is this functional called phi G. This is called Lettinger-Ward functional, right. This functional phi depends on only on the self green functions and interactions. It does not directly depend upon one body operator. So, that is why we call this functional is a universal functional. One other properties of this functional is a derivative with respect to G, it is a self energy, and this if and phi G, that is why you are calling it a universal functional. But what we want a Legendre transform of that grand canonical potential in terms of self energy, which is a del phi by del G, and you get this, you get here omega t, right, where Fe is defined this. So, now the Fe you can see since just in the last slide G was a functional of self energy. So, Fe whatever this we call this is a Pothoff functional. F is a Pothoff functional. Pothoff functional depend upon just self energy. This Pothoff functional is also satisfy if you ask the stationary solution of this will give you Dyson equation. This has also some sort of a universal, this is a universal function, because there is no one body term existing directly here. So, the method what Kitaev proposed, to see you can construct, you have a Hamiltonian H, original Hamiltonian, you can construct a reference Hamiltonian which should share two body interactions, whatever two body interaction you have in your original Hamiltonian. If you are able to do for that reference system, only difference between your original system and this reference system is one body operator, right? And that one body operator you can treat as a variational, right? So, what is the method? So, what we are saying, is that instead of writing this Kitaev functional for the original problem, you do a Kitaev functional for your reference system. What is the reference system in our case? Is a 4-side cluster. So, compute Kitaev functional for the 4-side cluster and then compute your grand canonical functional, grand canonical potential functional via this formula, where this G will appear just a green function of the cluster. So, now it is a very good, because one body operator is a variational parameter, and that is the way we do in the mean field theory if you are interested in studying a broken symmetry phase. So, T prime, the hopping on the cluster you can treat as a variational parameter. Chemical potential on the cluster you can treat as a variational parameter. If you are interested in studying a broken symmetry phase, you can introduce D wave, S wave, P wave, all sort of things on cluster, and ask the in that parameter space whether you find extremum of this or not. If you find extremum of this, take that value, put in the original model, you solve the problem. So, you modified the cluster perturbations theory. Okay. So, like this, if you introduce a m on the cluster and you do all this procedure, you find omega versus m at different u, and you can see minima is coming here. Collect this minima, this will give you the solution. Similarly, you can change the cluster size and look how this grand canonical potential as a function of m is changing. So, this is extension of CPT to actually capture other kind of a broken symmetry phase. That is why we are calling variational cluster perturbations theory. The advantage is this, you are not factorizing the short range interactions, and but spatial correlations of course you are missing here. This method works, and many kind of result the group who developed this they have produced. So, approach is the numerical approach is choose the Weiss field corresponding to your broken symmetry phases which you are interested, means you programmed in your cluster, then you compute this functional, optimize in the parameter space, then calculate the properties of model, very simple. And this is the way you introduce all the Weiss field if you are interested in superconductivity, D wave, S wave, X y, right. Cluster dynamical mean field theory is a different. Cluster dynamical mean field theory, what you do, you imagine a cluster is embedded in environment. You integrate the environment, what you will get a impurity Anderson model generalization of a cluster. This was discussed, and you must have listened in many talks. So, I am not going to describe this, but there is this point which I am going to highlight, which we call cluster dynamical impurity actions. So, if those who have used the dynamical mean field theory, you know the dynamical mean field theory in some sense is like a mean field theory, you iterate it self consistently, you solve it. But in dynamical mean field theory, advantage is this, the cluster is embedded, immersed in the bath, and you parameterize the bath in such a way that you want to get the result. So, you program your thing in the bath. Variational cluster perturbation theory, as you just listened, that you do not have a bath, you have just a cluster, you introduce the parameter and you ask the in parameter space what the grand canonical potential minima you have, right. So, now take a this kind of things, cluster immersed in the bath also. So, in the cluster dynamical mean field theory, you cannot introduce a Weiss field corresponding to broken symmetry phase on the cluster. You can only introduce in the bath, but here you can introduce. This is the method I have used, and sorry for this technical difficulty. Now, cluster dynamical mean field theory, in the case of a square lattice, if you study, we know the mode transition is a first order transition. Cluster dynamical mean field theory will not show the hysteresis, but cluster dynamical impurity action method shows the hysteresis. So, you can see the hysteresis, but in CDMFT no hysteresis. You can see on honeycomb lattice is a hysteresis, but on the cluster dynamical mean field theory is a jump, no hysteresis. So, it has advantage, more powerful, but numerically at least 5 times expensive than the cluster dynamical mean field theory. Okay. After doing this, the model Kitaev Hubbard model what you have, as I told you, t prime equal to 0 was a graphene. So, the fake result or the mistake of the numerical calculation spin liquid will not be here. So, it is going directly from metal to spin liquid. It is a metal to antiferromagnet. As you keep changing t prime, when you hit t prime equal to 1, this is the region where Kitaev, in the large U limit you can get a Kitaev model. So, you ask question, as you change U, what will you get? So, what you find, which SM is a short, is a semi metal, and ND means a Dirac points. In this regime you have a Dirac points 2, in this regime you have a Dirac point set and 2. This I am not going to discuss, because this is a separate paper. So, it's a paper wise talk. So, this is a metal to spin liquid. How do you say that is a spin liquid? This method what we have used, we computed a staggered magnetizations. A staggered magnetization is 0. Then you can say, so what? How can you claim that is a spin liquid? You are right. This method cannot tell you whether it is a spin liquid or not. But this method just giving you hint, there is no staggered magnetization. But we know that in the large U limit, this is exactly Kitaev model. So, in the large U limit, you know what happens. So, what we did to claim that this phase is really algebraic spin liquid, what we did is the following: that take a Hubbard model, the corresponding Hubbard model what we are doing, and do canonical perturbation and generate spin term, spin Hamiltonian of all order, T square, T4, T6, T12, you can do on computer, but only you can write on the this slide for second order and fourth order, 6th order, 8th order, 12th order you cannot do. So, I am showing you this, I am not going to discuss, because I prepared a talk 40 minutes, so I am not going to extend my time. This is all method, numerical method. So, if you do that, you will get a second order Hamiltonian is this, where when t prime is equal to 0, you can see this is just a Kitaev model, right. And when t prime equal to 1, it is a Kitaev model, because this term Heisenberg term is 0. So, this model is giving you Heisenberg Kitaev model when you are asking low energy theory up to T square. When you suppose you want higher order term, then H4 is this, only one term will be looks like a Kitaev and rest of the term is a different, and H6, H8, but difficult to write on the slide, but you can see in the form of number on computer. So, what we did here, since we know the Kitaev model is exactly solved, and all this term which appearing is a small term in the Hamiltonian. So, use that idea of exact solvability, solve that problem. So, how do you solve Kitaev model exactly? By Majoranaization. You do just Jordan-Wigner transformations, you introduce a Majorana fermions, you can solve it. So, this is my Hamiltonian, but you know the solution of this Hamiltonian, right, and I am interested in knowing H2 plus H4, and this is a big Hamiltonian. So, I cannot solve, nobody can solve. So, what I do is treat this just H2 exactly and rest of the term in the mean field level, and if you do that by the same method what Kitaev did, and ask what is a excited band dispersion for the spin-on. So, as a function of u, you can find spin-on dispersions which is shown at u equal to 2, but we have computed 2 to infinity, and we showed that 2 to infinity this Dirac point is intact there. So, whatever thing is there is really some sort of a spin liquid, and at the same time you ask what are the spin-spin correlation. In the same procedure you can compute a spin-spin correlations. And that correlations decay like 1 by r to the power 4. So, this is a like algebraic decay. So, we say that this is a algebraic spin liquid. So, we have used 2 methods, 3 methods. One, numerically we generated the effective Hamiltonian. Second, we use a cluster dynamical impurity actions, variational cluster and cluster dynamical mean field theory. Then we use this Kitaev mean field theory, and we showed this a stable algebraic spin liquid phase exists in this model. This is the only model you can see the metal entering into the algebraic spin liquid phase in interacting fermion system. Okay. One other thing which I did not discuss in my introductory part is that this model breaks time reversal symmetry, because you allowed a spin dependent hopping. But Mott insulating phase restore time reversal symmetry. When Daimler wrote a paper for using this kind of a laser you can get a effective Hamiltonian, he found an extra term which behave like a spin. Then he pointed that okay, once you have this Hamiltonian you can apply a reverse magnetic field and you can remove it. But he did not observe in that paper, if you do a perturbation for fermionic case you will not find such kind of a single term. Only you will find such kind of term when you are doing a bosonic term. So, we proved mathematically here, which I am not going to discuss here, that this we have proved that Mott phase of this Hamiltonian is a time reversal symmetric to all order of perturbations theory. We went up to the 24 and 28, and numerically we have shown that this only symmetric term is appearing, all non-symmetric term is disappearing in this. Okay. So, in summary, this model has a many kind of a phases. One interesting phase which I have just pointed is this algebraic spin liquid, but this method is a marriage of many kinds of a method. You can say what are you doing sir, for this you are using CDIA, for this you are using Kitaev mean field theory, for this you are using this. So, I can say I do not have a very unified method, but such kind of a thing you can do variational Monte Carlo. I do not know whether a sign problem will come or not, but that kind of issue you can address. But at the same time in Monte Carlo, how will you say that excitation is a Majorana fermion? Might be Anders Sandvik may shed light on this which in his talk. Okay. So, these two are my student and collaborator R. Shankar. So, you can identify this very beautiful beard, and then this is David Seneschal. The work published in all 4 papers, this. Thank you for attention.
Time for questions.
Title of your okay. Title of your talk: a topological Fermi liquid, algebraic spin liquid transition. Where is the topology?
Yeah. Is it there? Topology is there. Only we have to see. That is why the condensed matter is simple, only problem in seeing. If you see that the way you see, you find a phases. So, I will try to show you. Okay. So, as you told you, as I just mentioned, t prime equal to 0, this is just a graphene, right. So, it does not break time reversal symmetry, right. So, now as you turn on t prime, I mentioned it breaks time reversal symmetry. So, if it breaks time reversal symmetry, you can ask the question, any non-trivial topology appears or not. So, topology and geometry competes, right. So, now here you can ask, okay, let us this phase, right, this model, right. So, this band. So, now you ask whether each band has a non-trivial Chern number or not, whether it is a 0 or 1, 2. So, it was computed, it is a Chern number 1 plus 1 minus 1. Now, imagine, so this is a well-defined Chern number, not like a graphene. Graphene you cannot define well-defined Chern number, but in this model at T prime equal to 1, you can define a well-defined Chern number. So, suppose you are not sitting at half filling, right? You are just sitting little bit away from half filling, and you ask what is a integrated curvature. Curvature, when I am taking curl of your Berry potentials, right? That will be a Berry phase. So, this Berry phase is this, right? So, you can say as you turn on. So, this phase diagram, if you see, which I have talked earlier ICTS. So, that is why this is not good that talk same thing twice. This blue curve I have not discussed here, right. This blue curve is going from Dirac points 8 to 2, right. This is a Lipschitz transition, one thing. Second thing, what you are finding here, this phase, this semi-metal, what I am calling, this semi-metal breaks the time reversal symmetry. If you dope this system, right, you can say this is topological Fermi liquid.
Okay, any other questions?
So, yesterday night I thought that I will not do the justice to my talk. So, remove this all topology, because there are experts sitting here came from the Sat Samundar part to talk this. So, why should I talk?
Okay, if there are no further questions, let's thank the speaker once again and move on to